So here's the resonance structure of the perchlorate ion. It's one of our first polyatomic ions that we made flashcards for. The idea of a resonance is that there's more than one form of the molecule, and each form is equivalent. That is to say, not one form is biased towards the other. So here we have multiple structures, each one equivalent, and also that minus charge in a lot of these formal resonance structures, is delocalized. So it sort of buzzes around the atom, the outer atoms, shared equally, that is to say. So Cl has a happiness at 7 valence electrons. Cl is happy at 7. Oxygen is happy at 6, but we have 4 of those, so that's 24. And then that minus sign symbolizes 1 electron gain. So we have here a total of 32 valence electrons that we have to accommodate to make the ClO4 minus perchlorate ion molecule structure. So let's make Cl our central atom, realizing that any of the 4 oxygen atoms, we don't know which one of the 4 can be central. So a Cl will be the central atom, and then we have 4 oxygens that are the substituents around it. All right, the minus sign automatically tells us that minus formal charge symbolizes a single bond to an oxygen, right? So 1, 2, 3, 4, 5, 6, 7, 8, okay? And so the formal charge for a single bonded oxygen, let's look at the formal charge consideration for this oxygen atom here. So 1, 2, 3, 4, 5, 6, 7. Formal charge oxygen happy at 6. 6 minus 7 is minus 1. So there's our minus 1 formal charge that will go into there. And then the other ones are going to be double bonds to get it to a 0 formal charge. So we'll put a double bond here, and instead of 3 lone pairs, we'll have 2 lone pairs. We'll put a double bond here, so instead of 3 lone pairs, we'll have 2 lone pairs. And ClO4 minus, here's our minus. So instead of a single bond here, we'll have a double bond, and we'll have 2 lone pairs on the oxygen atom. Okay, so once again, let me tell you that formal charge calculation again. 1, 2, 3, 4, 5, 6, 7. Oxygen happy at 6. 6 minus 7 is minus 1. What about the formal charge for this double bonded oxygen? 1, 2, 3, 4, 5, and 6. Oxygen happy at 6. 6 minus 6 is 0. So that's how you want to do that. And even the octet rule is fine here. So the octet rule, 1, 2, 3, 4, 5, 6, 7, 8. So the octet rule is satisfied. And even it's satisfied here, right? 1, 2, 3, 4, 5, 6, 7, and 8. So for the octet rule, you're going to calculate everything as 1 individual electron for the octet, because this is shared equally. Or if it's a polar molecule, it's shared not so equally. What about the formal charge for this chlorine? 1, 2, 3, 4, 5, 6, 7. Chlorine is happy at 7. 7 minus 7 is 0. This is an expanded octet, though. The octet is going to be expanded. It's not 8, but that's okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. In fact, that's a very expanded octet for the chlorine to make the ClO4 minus. Well, that's the only way we can get the minus formal charge. And we want the minus formal charge on the outer atoms. Okay, we want it on the outer substituents rather than in the central atom. So that single bond on the oxygen can also be on the top. It could also be on the left oxygen. It could also be on the bottom oxygen. So that is where resonance comes in. So I already drew it on the rightmost oxygen. So let's have it at the topmost oxygen. In order to do that, we will pull this pair of electrons here and kick this pair of electrons out. So now we have the single bond on the outermost oxygen, or excuse me, the topmost oxygen. So let's go ahead and draw these resonance structures. Right, so we have our first one. Our single bond is on the rightmost side. Let's just put it so that our single bond is at the top. So I did not mess around with any of these other oxygens. All right, let's highlight our single bonds here. Okay, so single bonds and that minus formal charge on the ClO4 minus is really being delocalized. Okay, let's have it now on this leftmost oxygen. So let's pull this double bond here and kick this pair of electrons back to this leftmost oxygen. So doing that, we'll get our another resonance structure. Okay, now the formal charge is on this oxygen. Let's highlight where that single bond is, and also that minus formal charge. And finally, our final resonance structure is where the single bond is shared at the bottommost oxygen. So let's put this pair of electrons there to get a double bond, and kick this one out here, and then the double bond is now on the leftmost oxygen, but the single bond is now on the bottommost oxygen, sort of equally shared across all of the oxygens. Okay, don't forget to close your brackets. And here is that single bond on that oxygen. Here is the minus formal charge. Again, the key word here for all of resonance structures is this idea or this concept of delocalization. In delocalization, the minus charge and the double bonds and the single bonds are equally shared and equally buzzing around or equally delocalized across all of the outer atoms. And here all of the outer atoms are the same oxygen atom. It imparts tremendous stability to a lot of these types of resonance stabilized ions. It imparts tremendous stability to these hybrid structures. Not one form is biased towards the others. In other words, all of these structures are equivalent. They're the same, and that minus charge is sort of buzzing around each of these four, delocalized across each of these four oxygen atoms.